This is the example of computing factorial using a recursive function. So this is again the same example we saw in the slides. At the very top, we're including the standard IO library. We have the function prototype for the recursive factorial function, taking an unsigned integer as argument and returning an unsigned long integer. In the main function, we have a loop that right now goes from 0 to 21, incremented by 1 in each iteration. Counter variable, loop control variable is I, and that value of I is passed as an argument to the factorial function. And inside the for loop, we have a single printf statement that prints out so basically the value of I factorial equal to and whatever the value returned from the factorial function is. And we have a return 0 statement at the end that I added. The factorial function itself consists of an if block and an else block. If the argument received in local variable number, if that is less than or equal to 1, this function returns a 1. So this is the base case. In the else block, we have a recursive call to the factorial function with argument number -1, less 1. Multiply, and it returned, and that is the result of the value returned by the factorial function is, of course, multiplied by number, and the product is returned. So let me run this one time. And you see the same output that we saw on the slides. Let me show you now what happens when I let this, or at least try to run this loop up to 22. And you see over here that if I multiply the 21 factorial value by 22, I should get a number that is at least one digit greater than the value of 21 factorial. That is not the case. What is happening over here, I have an incorrect result. And what we're getting over here is basically the data type that we have chosen for storing the result of the topmost factorial function is simply too small for the number that we're trying to fit into it. And if you're skeptical about that, let's try to run this loop up to 30 and see what happens. And there you go. You see that all of a sudden the value that this factorial function is returning is saturated at roughly a certain number of digits, and the number is not growing as quickly as it has to. So this shows you that at factorial 20 actually, factorial 21, that is the largest factorial number that we can compute using. So let me also take this opportunity to show you how the size of the function call stack grows in factorial functions. So let me add a breakpoint to line 8, the printf statement in the loop in the main function, and run this up to here. Now let me step into the factorial function. Initially, this is for I equal to 0. Keep an eye on the function call stack down here in the lower right corner. So initially, it's not going to be much. Keep stepping now, and I'll do this rather quickly. Okay, so this is for I equal to 0. Now we'll do it for I equal to 1. Also pretty straightforward. Now let me go in with I equal to 2, also pretty straightforward. But you can see now for I equal to 2, the function call stack is getting larger. Let me keep going. We are now at, I think, I equal to 4 right now. Actually, I cannot tell what the value of I is because I'm in a different scope. I'm in the factorial function, but you can see the function call stack right now has uh, uh, four, uh, 4 frames. Keep going. Okay, so now with I equal to 5, see how large the stack grows. So you can see I already have 5 frames over here, 6, and now they start returning values. Return, return, return. And when I now do this for I equal to 6, the function call stack will grow even taller. Just one more for I equal to 7. There you go. So you can see that the whole function call stack, actually you have to scroll down to see the bottom of it, is taken up by recursive calls to the factorial function. Let me get out. And there we are, back out. So I'm going to remove the breakpoint now. I'm going to hit the F5 button so this finishes execution. And here's the output again. Let me now jump to the other example that we had, the Fibonacci series. Similar idea. This one, the function call stack grows even larger because each call to Fibonacci spawns 2 more calls. So this is exponential growth. First, let me run this as this. So let me enter a small integer, let's say 10, and you can see that the answer came back fairly quickly. We try something larger, 20, still came back fairly quickly. So you may think that it doesn't seem to be much of a problem. Let me try 30. Still very fast. 35. Now this, if you notice, this took a fraction of a second. Let me run this with 40. Pay attention. Still running. Still not back. And this one actually took a couple of seconds. Let me try 41. Running, still running, still running. And you can see this one took almost twice as long. Roughly, I mean, definitely longer than when I entered 40. Try 44, and this should take quite a while now. Still not done. Still not done. And we're still waiting. And we finally have our result. play around with it, and I won't do this here, but you can try running the Fibonacci sequence and stepping through it and see how the function call stack grows for this one. This one will grow even faster. For the value 10, you should have something like 1024 entries on your function call stack. That's enormous. So try it out, play around with it, and we'll move on to, and this basically completes recursion.